So, in the last class we discussed the effect of clouds on the earth climate system and how we are not confident about how an increase in carbon dioxide will change the global mean temperature, because we are not able to model accurately the way clouds will respond to global warming. So, today in this lecture I want to give examples from a few climate models to show why so much difference is there. Okay. So, in the first slide here I am showing you the two different climate models, one developed by Goddard Institute of Space Studies in New York by Hansen and his group, and the other one by the Princeton group of Weatherland and Manabe. Okay. So, in the two models, the feedback due to changes in cloud amount, cloud fraction, was very different. One of them got 0.33 watts per meter squared per degree Kelvin change in global temperature, other one got 0.12. This is a factor of 3 difference almost. Okay. The cloud height feedback, which alters the greenhouse effect, causes a much higher value of 0.4 watts per meter square degree Kelvin in one model, while it's only 0.25 in the other model. When you add these two, the amount feedback and the height feedback, you get 0.73 watts per meter squared in one model, will get 0.37, almost half. So, the cloud feedback difference between two models is a factor of 2, which is a very large difference. And so, this is what is causing large uncertainty in the prediction of response of the earth to the increase in CO2, and a lot of work is being done to see whether we can reduce it. So far there is not any great success. Okay. Now, why is that? So, look at the change in net radiation R due to one aspect of the cloud X, and that could be cloud fraction or cloud height or surface characteristic, and how that changes the temperature. This is the feedback which is bothering us. Okay. So, there is a non-trivial relationship between cloud and temperature. So, that is why response of clouds to global warming is highly uncertain, because various aspects of clouds, the cloud type, the cloud height, the cloud fraction, cloud characteristics affect the net radiation feedback. Okay. Now, here is an example of how cloud feedback varies in space. Okay. There is a large variation. There are places where the feedback is positive, the other place feedback is negative. Near polar region it is negative over the ocean and positive over Antarctica. So, huge variations are there, and this changes from model to model. So, this is a major concern. Now, to show you how difficult the problem is, I am giving the example of one series of models called the Community Climate Model, developed by National Center for Atmospheric Research at Boulder, Colorado. They have developed a series of climate models over the last 40 years. The models had a positive cloud feedback in the earlier days, anywhere between 1 to 1.25, but as the model evolved and got developed, it became negative. So, the same model, as it evolved in time, as they changed various ways in which they modeled clouds, the cloud feedback changed sign. Okay. Same model, but slightly different cloud model. So, this shows how sensitive the model is to the way you calculate clouds and the way you model changes in cloud due to changes in CO2. So, this is the biggest uncertainty that we see from one group in Boulder, Colorado. Now, in that model we also can see the difference between long wave and short wave feedback, because they act in opposite direction. So, the earlier model CCM2 had a negative feedback in the long wave and a positive peak in short wave, and they sort of cancelled out. But a newer model, the long wave became positive, the short wave became negative. Okay. So, the sign of the feedback between long wave and short wave flipped, and ultimately the net feedback in both is negative, but for a different reason. Okay. So, the impact of cloud is so important that there is a quantity called cloud forcing. That is the difference between the fluxes in the cloudy region and the fluxes in the clear region. Clear region is denoted by 0, no cloud. Okay. The difference in cloudy region, no cloudy region is defined as cloud forcing or a cloud feedback, and this is a long wave feedback and the short wave feedback, and you add these to get the total feedback. Okay. So, based on satellite data gathered in the 80s, it was determined that the long wave feedback was around 30 watts a meter squared, short wave was around 47-48 watts a meter squared, and so the net annual feedback was minus 17 to 18 watts a meter squared. So, this is the one which already mentioned in the earlier lecture, and this is the impact of clouds. Okay. In the long wave is positive, short wave is negative, net is negative, and you can see that the slight difference between the two hemispheres and the difference between different seasons also. Okay. So, the northern hemisphere has a lesser net effect than the southern hemisphere. Okay. Remember, the southern hemisphere has more ocean, so it has hardly different cloud response than the northern hemisphere. Okay. Now, let us look at the same thing in graphics. You can see that in the global mean picture, around 340 watts a meter squared per unit area of the earth comes in, about 100 watts a meter squared is reflected, and the earth surface emits around 390-395, and what is going out is 240. Okay. Now, this is now separated into the short wave effect and the long wave effect. Okay. And the difference between clear sky and cloudy sky are separated here in short wave and long wave. So, this is close to what we discussed in the last slide. Now, this is repeated again in this slide, showing that short wave effect has a positive impact of 48 watts per meter squared, long wave is negative, and this total is positive here. So, I must warn you, the sign convention is not the same as in other. This is still causing cooling, but the sign convention is positive. Okay. I want you to remember that. And the CO2 increase from 1750 to 2005 is a positive effect of 1.6, but the clouds effect is much more than CO2. Now, let us look at the cloud impact in terms of various cloud parameters. Okay. For example, if there is a 50% change in the low cloud amount, you will get a negative effect, cooling. If there is a 50% change in the high cloud, cirrus clouds, which trap Earth radiation, it will be a positive effect. Okay. If the cloud height increases by 50%, it will cause positive effect. If the cloud thickness or optical depth increases by 50%, it causes cooling. If the particle size in the low clouds increases by 50%, it will cause warming. And aerosol effect, very complicated, we will discuss that later. Indirect effect can cause slight cooling, direct effect also cause slight cooling, very small amount. Ozone changes, which are not discussed so far, causes warming. Changes in land albedo due to deforestation or forest fires cause cooling, and carbon dioxide, which is a major driver, is positive. So, what I want to say is each individual term here is much larger than the effect of carbon dioxide. That is why it is so difficult to predict how the Earth's climate will change in response to carbon dioxide, because carbon dioxide is the major forcing, and the cloud feedback effects are much larger than the forcing by carbon dioxide. Now, all this complexity of clouds can be shown by this following thing. Cloud interaction can affect the clouds through changes in cloud fraction or how clouds overlap the low and high cloud. That is very important. You have to model that correctly. Then how cloud top and cloud height change, that alters the reflectivity and the greenhouse effect of clouds. Then you have the amount of ice or water in the cloud condensate, how much it is, that affects the cloud feedback. These are all cloud macrophysics, the large scale effects. Then you come to cloud microphysics, the role of whether the condensate is ice or liquid water. This is the amount of condensate. This is whether the condensate is ice or cloud, that alters the feedback. Then you have the cloud particle size, whether ice or water, the change will cause further problem. Then you have cloud ice particle shape. In the case of liquid droplets, there is no problem, they are all spheres. But in the case of ice particles, they come in a variety of shapes, and the shape has an impact on reflectivity of the cloud. Then you have to worry about the distribution of condensate, how the condensate distributed horizontally and vertically. And finally, in what environment the cloud is. The way cloud behaves in the tropics is very different from the same cloud behavior in Antarctic or Arctic, because the environment is different. So, when you talk about cloud, you have to talk about cloud in relation to the environment in which the cloud is embedded. Okay? So, that is a very complicated issue. So here you see the cloud macrophysics, the cloud microphysics, and the environmental influence affects the cloud both through microphysics and macrophysics. Yes, now let us compare satellite data, which have provided an accurate estimate of what clouds are doing, and let us look at the tropics, where clouds play a very important role. You can see that the changes in cloud fraction as measured by the satellite MODIS agrees very closely with the cloud albedo as measured by Ceres satellite. Okay? So, what this shows in the tropics, the changes in albedo of the clouds is very closely connected to changes in cloud amount. Okay? That is a very good news. That means, if your model is able to correctly predict the cloud amount, you will get the answer more or less correctly. When you go to the global case, also a similar result is valid, and you can see that the global mean cloud fraction as obtained from MODIS agrees with the changes in albedo, which is in the green. Okay? So, albedo change in the green and the cloud fraction in red, and they are very closely matching. So, the global mean cloud fraction is the dominant factor which affects the albedo of the clouds. Now, let us summarize the role of clouds. Low level clouds increase the reflection. The greenhouse effect is small, because low clouds, the cloud top temperature is very close to the ground. So, greenhouse effect is not much. So, the major role of low clouds is to cool the earth, and that dominates the climate change. The high level clouds cause a large greenhouse effect, okay, while the reflection effect is very small. Okay. So, they warm the earth. So, high clouds warm the earth, low clouds cool the earth, and today the net effect is cooling. But you look at deep clouds, the reflection is very large, they cause large albedo change. The greenhouse effect is also large. So, the two almost cancel out, the net effect is 0. So, we must really worry about not the deep clouds, but the shallow clouds which change reflectivity and overlap of the clouds. The same way you can put this in this graphic. The cloud feedback is due to temperature or the cloud top in the case of long wave, and in the case of short wave it is due to not much change in albedo, but the change in cloud top temperature. Now, let us look at the simulation by about 18 models given in this paper by Zelnicka, and what they are showing here is the total effect. We will come to that little later. Effect of cloud amount, effect of cloud altitude, and effect of optical depth, and it is shown in terms of effect on short wave, long wave, and net. Let us look at cloud amount, and we see the total effect, and this is the upper troposphere and lower troposphere. Let us look at now total effect. So, the big effect amount is around 1 watts per meter squared, sum of long wave and short wave. Okay. While cloud top altitude, effect of short wave is not much, effect of long wave is much more. And if you look at optical depth, thickness of cloud, the short wave and long wave are in the opposite direction, the net is slightly negative. Okay. So, from this picture you get the clear feeling that the major impacts are in cloud amount, okay, and the long wave, short wave are different. So, that is sum of these two. So, recently a paper appeared a few months ago combining many models, the total cloud feedback, all long wave, short wave, high, low, everything put together. And what I wanted to see is that most of the models agree on the total cloud feedback being anywhere from 0 to 1 watts per meter squared, except for one model and another model here which is outside the natural variability range. So, other than that, most models agree that the total cloud feedback is close to the observed value that was been analyzed for the last 12 years here. Okay. So, that is good news that today the models improved a lot. There are except for 2 or 3 models, most of them agree on a total cloud feedback on radiation budget. Now, here is a comparison between different models now with more detail, covering high cloud, medium marine cloud, tropical annual cloud, low liquid amount, middle liquid amount, and high amount. Now, I would argue that by and large the models are doing well, except one can clearly see that tropical marine clouds are not doing well. Now, you must remember that low cloud is the most difficult to simulate in a climate model, and that is why most models are bringing values outside the range of observation. Observation ranges values are here, and the grayscale is the range, and the models are well outside it. So, that is the major problem regarding marine low cloud amount. Now, we will compare the role of long wave and short wave cloud feedback in terms of the visible optical depth, okay, and cloud top temperature. These are the two things which affect the cloud, and as you increase the visible optical depth. That means you are reflecting and absorbing more solar radiation. The short wave cloud forcing goes on increasing, okay, and reaches a value as high as 300 watts per meter squared. But there is a sharp change here around 273 Kelvin. This you must recognize as being the role of ice. Below this height, clouds are water clouds. Above this height, these are ice clouds. Okay? And so, there is a sharp change as you go from water clouds to ice clouds. Okay? Now, when you go to the long wave, that change is not seen, because as you go from water clouds to ice clouds, the cloud top temperature is of course changing, but it does not change much with the optical depth. Okay. So, you can see that I want you to look at these two graphs closely. Here there is a rapid change due to change in optical depth. Here there is no change, the change in terms of cloud top height. So, the long wave is influenced by cloud top height, the short wave is influenced by optical depth, two different parameters about the clouds. So, when you combine these two, you get a very complicated thing here. Okay. So, this complex picture can only be understood when you resolve the short wave and long wave, and notice that in the short wave, cloud top height plays no role, optical depth plays a role, while in the long wave, optical depth plays no role and the short wave effect, the long wave effect is mainly due to cloud top height. The height effect is seen here, effect of cloud absorptions can be seen here, and the combined effect is fairly complex. Okay. And there is a line of 0 which we discussed. The 0 line is there when the two effects cancel out. Okay. And that we saw in an earlier slide, and this is a little more colorful. Now, I am going to compare two different models to highlight why models differ so much. So, one model is the Japanese model MIROC, high resolution model, and the other is the National Center for Atmospheric Research, Boulder, Colorado, well known center for cloud modeling and climate modeling. Both of them ran model with a 1% increase in carbon dioxide, okay, for a long time until CO2 was doubled. Okay. This was an important project of ocean atmosphere GCMs. So, the surprise was the Japanese model produced a 3 degree Kelvin warming, while the NCAR model only produced 1 degree warming. So, it is a huge difference. Okay. Remember that 1 degree warming is going to happen at the end of 70 years, we will say okay, we can manage to live. 3 degree warming will cause major changes in the Earth's climate system. So, we would like to know why this difference is coming for the same change we introduced. Okay. So, this can be understood through cloud radiative forcing and total cloud. You can see that in the Japanese model, cloud radiative forcing is positive or the order of 1.5 watts per meter squared, while in the American model NCAR, it is minus 1.5 watts per meter squared. And why that happened is visible here. In the Japanese model, the clouds increased, and the American model clouds decreased. So, you can see clearly how changes in cloud fraction changes the sign of the cloud impact. Okay. If the clouds increase in the model, the reflective will go up and the model will not warm so much, while if the clouds decrease in a model, you have a large increase in temperature. So, those who are hoping that somehow the earth will increase the cloudiness and adjust to the CO2 warming, we will realize that NCAR model is not showing that. We do not know what the truth is. Truth may be in between. Okay? So, the expectation that somehow the cloud amount will increase and it will reflect more radiation from the earth to counteract the trapping of earth radiation by CO2, it may not be true because two models show two different results. So, this is the major lesson, major understanding for the fact that models do not agree on the changes in cloud fraction. And in the last 40 years satellite data, we do not have an accurate enough information to tell whether the cloud fraction has decreased or increased. The change is very small right now. The change will become larger later, but we are not yet able to get the signal. Okay? So, let me summarize. The total feedback equals the sum of contribution from different feedbacks. Okay? The largest negative feedback is due to earth warming, is called the Planck feedback, and that all the models agree on. Okay? Now, additional warming is due to long wave emission to space. Okay? And then we have increased greenhouse effect by water vapor, which is a positive feedback, and then increased reflection of solar radiation due to albedo feedback. There are 4 of these. They will be of opposite sign, many of them. So, the net is what we are looking for. Okay? Each one is large, but the net will be sum of positive and negative values. Now, you can see that the 12 models compared here, okay, they have almost same Planck feedback of the order of 1.1 watt meter squared due to CO2 doubling, which we saw in earlier results. Then we have the water vapor plus lapse-rate feedback, which is slightly varying, but almost common. Then you have surface albedo feedback due to melting of ice and snow, that is quite small and same value. Then you come to cloud feedback, which is almost 0 in model number 2 and very large in model number 12. So, this is a major uncertainty. The cloud feedback is the largest uncertainty in these climate models, and work has been going on this for the last 40 years, but models do not agree on the amount of feedback. Now, this one shows the result even more dramatically in color. Various models are shown in colors, and the first one is albedo feedback, which most models agree on. Then this is water feedback, all of them agree is very large and around 1.75. The lapse-rate feedback is the opposite sign, minus 0.5, slight difference, but when you add these two, the difference goes away. So, what you must realize is the albedo feedback due to ice water melting and the combined lapse rate water vapor feedback, all models agree. Okay? Now, you look at cloud long wave, cloud short wave, they do not agree. You see the net feedback, huge differences there in total cloud feedback. The Planck feedback, no problem. So, Planck feedback, no problem. Lapse rate, water combined, no problem. The albedo feedback, there is no problem, but cloud feedback is a major uncertainty. There is a huge difference from a low value to high value. We are not able to settle the issue, and although we have 40 years of satellite data, the cloud fraction has not changed sufficiently for us to find out which model is right. Okay? Now, this we will go back to this slide which we had, which shows how the initial 4 watts a meter squared forcing by CO2 provides many responses: water vapor change, snow as ice change, cloud change, and vertical profile change. So, ultimately we are getting 3 watts, but 3 degrees centigrade, but the change is due to certain addition, certain subtraction of various feedbacks. Okay. So, the feedback to CO2 doubling is very complex, and the largest uncertainty is due to change in the cloud. So, I summarize by saying that cloud radiative change that accompanies CO2 induced change is a little complicated, because some of the changes occur very quickly, the cloud changes that according to our definition should be part of the forcing, because it occurs within a few days of the change in CO2. But the other change, it occurs due to change in sea surface temperature, is a feedback. So, feedback is really the more important thing. The clouds cause uncertainty in both forcing and feedback, but the feedback is really the more important thing. And the changes in cloud property are mediated by increase in global wind temperature, and that influences the feedback. Now, here is a comparison between again two different models. Surface albedo change, large difference here. Water vapor change, not so much. Cloud cover, very large difference, we saw that, and the total is almost same here in this case, because there is cancellation between this and this. Okay. This is one example, very old one. And here is one model, various feedbacks, and you can see that finally, when you see the feedback cumulative, the error range is 1.4 to 4.4 degrees Kelvin, because of a large variability in this. Now, this we already saw, I will skip this slide, between two different models. I am sorry, this is also same. And yeah, here I want to highlight the big difference in the same model by the UK Met Office, but different cloud feedbacks. So, they did one experiment, okay, in which the cloud particle size is calculated based on cloud liquid amount, okay, and an empirical model, and then the next experiment differs from B, is based on subcritical scale cloud liquid water. Okay. Now, you can see the three experiments conducted show very different temperature change, because the cloud forcing is very different. Same model with different specification of the cloud scheme causes either a cooling of half a degree due to cloud feedback or a warming of 0.66. So, this particular example highlights the great challenge we face, that the same model with different specification of way the cloud particle size changes has a huge impact on the temperature change. So, this concludes the discussion on cloud feedback. We realize it is a very complex problem, a lot of work has been done, a lot of observations made, but still the problem is not resolved. So, the policy makers must understand this when they decide on the policy about what will happen in the future. Thank you.